Hey folks, welcome back. Hopefully your Wednesday was a good day for you and you were able to feel pretty confident with that quiz. Today we're going to talk torque and cantilevers. So basically what that means is that we're looking at kind of Brian on a beam, but um, it's just a subtle difference to it, subtle change to it. Okay, so when we look at cantilevers and torques, okay, what we're going to see here, whoops, sorry. All right, is that if we have, say, a plank secured to a wall, and now I know what you're thinking, like, okay, what's the real world application of this? The real world application of this could be construed as like putting an awning over a storefront, okay, or securing like in kind of an old school style um, roof just over the sidewalk of something, right? That's really what we could look at here and consider it a cantilever, right? You also, I suppose, could talk about how much force is needed on like that first diagram that we saw, where the person was sitting on that kind of cliff edge there, all right? And again, I know I've asked this question before, but back here, sorry, would you would you be all right sitting out there, feet dangling over, you know, position like that, probably looking at the mountains behind a little ways up, or even on the left side there. Is that all right for you at Willis Tower in Chicago? Anyway, here we go. Okay, so if the beam is 4 meters long, homogeneous, and weighs 50 newtons, how much torque is there about the yellow fulcrum due to the beam's weight? Now, here again, when we look at the concept of this beam, right, we're still very similar to Brian on a beam. So anytime we talk about that horizontal surface and that beam concept, like we did in Brian on a beam, right? The reason we say it's homogeneous is because it's the same throughout. For us, that's a big deal because when we talk about this thing being uniform throughout, we can still find the center of mass or the center of force for us. Okay? So when we look at this, where does all the weight of the beam act as though it's concentrated? Meaning, like, if we were to try and balance this beam out, where is that location going to be? It should be right in the middle, all right? And that's still the big concept for us. So when we're looking at this, it still should, because this is a horizontal beam, because the center of mass, because the location where we can kind of create, a minimal amount of twist out of it is going to be at 2 meters, all right? That's the average location of the beam's weight, meaning if we want to think about it, you can basically, if you look at the whole entire beam, it balances out by taking a slice off each end, slice off each end, slice, slice, slice until you get to the middle. All right. I don't know if that makes sense or not, but it's one of those things that's where the weight is really, really going to be focused upon. Okay. So we see a 50 Newton force at 2 meters. So in order to calculate the torque here, what we're going to do is we're going to take that perpendicular force times the distance. So it's going to be 50 times 2. So what we'll see here is we'll see 100 Newton meters of force, basically trying to get that thing to twist down. All right. So even before we talk about anything else, that would be the amount of torque we would have to overcome just to get this sign to sit at that flat angle like that. All right. So we then ask, okay, how hard would you have to pull up at the end farthest from the brick wall to support this beam? Now, please understand, I get it, right? If we're looking at this green arrow here, that's vertical and it's 4 meters away. We would need an entire another structure up on the top of this thing in order to even talk about support. Likely we're going to put this on an angle, but for our purposes, putting on an angle is a little bit more difficult than what we want to accomplish. We want to get the idea of just this concept of torque up and torque down balancing out. All right. Now, if you decide to continue the pain of physics more, yeah, you'll see that. Great, whatever. Okay, but not here. All right. So we know that the weight of the board produces a downward torque of 100 Newton meters. So what we have to do is we have to be able to counteract that 100 Newton meters, right? So we have to be able to get 100 Newton meters of upward torque, all right? That way then that stays flat. So now if we know what our upward torque is going to be, and we know that the distance of this thing is going to be 4 meters yet, because that's the length of the beam, then we just start to do our torque equation. Now, I've rearranged it, right? You can if you want to. Otherwise, it's 100 equals the force times 4. So it's 100 divided by 4. So our force there should be 25 newtons of force, right? That's how much force we have to apply upwards in order to be able to get this beam just to stay stationary the way it is, right? So what we start to do then is we start to look at, all right, well, likely it's not physically possible for us to put something out at 4 meters, right? Because, I mean, that's over 12 feet. It's almost 13 feet away, right? So what if we put something half a meter away? Half a meter is about 1.5 feet away, about almost 2 feet off the wall. Could we put something there? Absolutely. So how much force would that require? So same concept. We know how much downward torque we have that we have to balance out at 100 meters. So all we do is we take our 100 Newton meters divided by 0.5. We would need a 200 Newton force. Now, 200 Newton force is somewhere in the neighborhood of probably about 45 pounds worth of force just pulling up. All right, just pulling that thing straight up. All right, so 200. Okay. So then, next one, what if we pull up at 1 meter? All right, 1 meter should produce a force of 100 newtons, right? So for that one, it's about 20 pounds of force. Okay. So what we start to see is that the further away that we get from this, the less force we have to actually utilize in order to keep this cantilever balanced. Okay. The closer we get, the more that force starts to really rise. You can think of it like a kind of, half of a parabola or an exponential growth equation, where the closer that thing gets to the fulcrum here, the closer it gets to 0, the more likely that thing is to spike, climb, go up real fast. All right. The only other way we can mess with you is maybe put a person out here, and then say how much force at the end do we need to balance out. Okay. Make sure you get out, try out, practice. Make sure you get out and do some homework on this stuff as well. All right. Talk to you.